the east side party like we do.
And can make this more clear. Maybe if we just write this out, this is going to equal I plus a minus lambda I times t plus t squared over 2 factorial times a minus lambda I squared, and so on. But if this is equal to 0, when we multiply it by v, and yeah, I forgot to do that. That's why. There's a v here. Multiply everything through by v. Put this t in the front instead. So since v times this is equal to 0, that'll go to 0, that'll go to 0, and then we'll be left with e to the ta times v equals e to the lambda t times v. Or sorry, yeah, that's correct. So that's not the case. Let's say if a minus lambda I squared times v equals 0, then we'll get e to the ta times v equals e to the lambda t times v plus t a minus lambda I v, and then everything after this point will go to 0. So this is what we'll get. So now we got to apply this to a system with repeat eigenvalues. So all of this was leading up to a system with repeat eigenvalues. So let's look at this system. For example, negative 1, 2, 1, 0, negative 1, 0, and negative 1, negative 3, negative 3 times x, and this is x prime. So if you look at the determinant of a minus lambda I, you'll get that the eigenvalues are 1 and then negative 2 and negative 2. So we know how to deal with this. This gives us an eigenvector. If we look at the null space of a minus lambda I, or a minus I, that'll give us eigenvector. In this case, it turns out to be 1, 1, negative 2. But this is what we're concerned with, this repeat eigenvalue. Its algebraic multiplicity is 2, and it turns out when we look at the null space of a plus 2i, we only get one eigenvector, 1, 0, negative 1. But we need 2 to get 2 independent solutions. So going back to this, if we used our matrix exponential to find the solution here, this would just be x1 equals e to the ta times b1. But because a minus lambda I times v1 equals 0, or in this case a minus I, because lambda is 1, since that's equal to 0, this truncates down to e to the negative t times 1, 1, 2. That's our first solution. So if we do the same thing on this, we can get x2 equals e to the ta times v2. But because a plus 2i times v2 equals 0, this truncates to e to the negative 2t times 1, 0, negative 1. We still need one more solution though. And the way we do that is we look at a minus lambda I, and this is lambda 2, lambda 2 squared. We want to find vector v3 such that a minus lambda 2i squared times v3 equals 0. So in this case, this is a plus 2i squared times v3. And then, if we do this, then we'll get a third solution, x3, which equals e to the t a v3. In that case, this will be e to the lambda 2t times v3 plus t a minus lambda 3i times v3. Everything else beyond that truncates because this will be 0. So let's go ahead and do this. A plus 2i squared equals 1, 2, 1, 0, 1, 0, and negative 1, negative 3, negative 1 times itself. This will give us 0, 0, 0, 5, 1, negative 8. And I'm skipping over the details just so you get the main idea of what's going on. We'll go over details more in the example video. So now we look at the null space of this. To find V3. So this gives us the augmented matrix. Looks like this. And row reducing that gives us 0, 1, 0, 0, 0, 0, 0, 0, 0. So this has dimension 2. So it actually gives us 2 vectors. The 2 vectors, the only condition is that our middle variable be 0. So let's just look at V3, which equals A, B, C. This only tells us that B equals 0, A equals A, and C equals C. So B3 is equal to A, 0, C. So this has 2 free variables. So it actually gives us 2 what we call generalized eigenvectors. So we could choose either 1, 0, 0 or 0, 0, 1, as long as our solution is linearly independent from V2. So choosing 1, 0, 0 gives us, so we choose V3 equals 1, 0, 0, and that gives us a solution x3, which is, as we said before, e to the ta, which equals e to the negative 2t times b3 plus ta plus 2i times v3. So what we can actually do is we can bypass this step altogether, finding v2 using a plus 2i, and we can just use these 2 generalized eigenvectors 1, 0, 0 and multiply both of these. Sorry, I should be multiplying this. Multiply both of these by e to the ta to get us 2 independent solutions. But since we already did the first step, we just need to do this with our choice of 1, 0, 0 or 0, 0, 1. So anyway, this turns out to be e to the 2t plus, or times 1, 0, 0 plus t times 1, 2, 1, 0, 1, 0, negative 1, negative 3, negative 1 times 1, 0, 0. And multiply this vector through, we get 1, 0, negative 1, and this gives us a solution of e to the negative 2t times 1 plus t, 0, negative t. So this is our third solution in our set of fundamental solutions. So now to go over the major points. If our algebraic multiplicity equals q, and it is greater than greater than 1, and it is greater than our geometric multiplicity, then find the smallest p such that a minus lambda I p equals 0, or has a null space with a dimension equal to q. So we want a dimension of the null space to equal the algebraic multiplicity, or the geometric multiplicity, in a sense, to equal our algebraic multiplicity. There's a little theorem called the Cayley-Hamilton Theorem. That says that matrix A must satisfy its characteristic polynomial. So this tells us essentially that a minus lambda I to the q power has to equal 0. This is guaranteed to be true. It's just that sometimes you can find smaller p for which this is true. So after you find that a minus lambda I to the p, which has a null space of dimension q, then you find a basis for this null space with vectors v1, v2, all the way to vq. And these are called the generalized eigenvectors. And then for each generalized eigenvector, we find a solution. And we'll call this xj of t, which equals e to the ta times our bj for each vector. And this will simplify to e to the lambda t times vj plus t a minus lambda I bj plus t to the p minus 1, where p is that smallest integer we can find, divided by p minus 1 factorial times a minus lambda I to the p minus 1 times vj. And that's what our solutions will take the form of.